our colleagues from the East Coast to come out to Silicon Valley. All right, welcome. My name is Don Seitz, class of '79. I have one or two of my classmates are also here in the crowd, so we are well represented, as are many, many other classes. Great to see such a great turnout. Very exciting panel discussion this evening. But before I introduce the panelists, just a couple of comments. One, to thank DLA Piper, and particularly Brad Rock, for hosting this evening's event with this beautiful space. And also to both the Princeton Club of Northern California and the Princeton Alumni Angels for co-hosting this along with Princeton Entrepreneurship Council. Speaking of the council, many of you might be aware, by the way, just show of hands, who attended the blockchain TigerTalks about a month or so ago? Good. Awesome. It's really exciting to bring more and more content to the West Coast, and we will intend to do quite a bit more of that as time passes. So comments and feedback is always appreciated. But as you then heard, certainly for those who were not at the session back in March, PEC's mission really is to engage the entrepreneurial ecosystem. There's many campus partners that are in the middle of this slide. And then we, of course, reach out to faculty, to students, increasingly to industry, and then certainly to alumni. And we are, our mission really is to engage along content of this sort, so a lot of programming and events around mentoring and around funding. And this is an eyesore of a slide, but let me just, well, particularly for people apparently in the West Coast, but no. But the intent is, as you just scan the left column, there is a variety of content, including TigerTalks on the Road, which is tonight's event. In October of last year, we held the first ever Tiger Entrepreneurs Conference. And anything in red on this slide, which is what I'd probably suggest you just focus on, are events that are coming to the Bay Area. So really excited that we're going to actually have a Tiger Entrepreneurs Conference out here, probably next April. Still working with some folks at the university on timing. But our intent is to bring content of this sort, of the conference, of startup roadshows. We're expanding the mentoring program, which is a flash mentoring program for primarily younger alumni to engage with more experienced subject matter experts of earlier years. And then on the funding initiative, really exciting. First, we have, of course, the Alumni Entrepreneurs Fund, and in fact, one of the startup panelists tonight is a beneficiary of the AEF funds. That's one funding mechanism. We do VC roadshows. We had a roadshow out here last April. We'll do a series of those, both in New York and Boston, and then again out here next year. And then really excitedly, as many of you know, the Princeton Club of Northern California launched the first chapter of Princeton Alumni Angels. And in fact, tonight, as we speak, there's a launch event in New York City, because New York City is now the second chapter of Princeton Alumni Angels, and there's more and more interest across the country from various regional alumni associations about angel investing. So, really excited to ask our panelists to come forward. And as they do, let me just introduce them very briefly. Jeff and Tom and Ajit and Brighton, come on up. This is a really exciting panel discussion tonight. We have four wonderful representatives to speak to computer vision and AI from a number of perspectives. Starting with Tom Funkhouser, who's a professor of computer science at the university, also heads the 3D Vision Lab on campus. And Tom will talk about the research that he and his teams are doing, and some of the applicability in the market space for that research. Then to Tom's left is Bryton Shang. Brighton is class of 12 and has a phenomenally interesting startup. Well, I'll let him tell you what it's all about. But really exciting, really interesting, and as I said, he originally received money from the AEF and has some exciting news to share about the growth of his company. And then to his left is Ajit Singh. Ajit works actually right upstairs at I guess it's fair to say, a Princeton-dominated venture capital firm, Artiman Ventures. And Ajit has great experience investing in this space. So I wanted to share, or have Ajit share with you, perspectives as an investor in computer vision and related technologies. And then finally, to the left is Jeff Rosedale. Jeff is a patent attorney, an IP attorney, and a startup attorney. And again, really excited to have an excited lawyer.
I'm Jeff Rosedale. I don't know who that guy is.
Oh yeah.
and for proof, my wife is back there. Pam Leckletter, class of '86. She'll tell you.
And that must be a little bit of jet lag. So I take full responsibility.
No worries, Don.
You're a much better looking guy. So with that, we'll have each of the panelists talk for 7, 8, 10 minutes, and then we'll have some microphones going around the room to answer questions. And then at the conclusion of the panel discussion, which will last about an hour, we'll resume the networking and catching up out in the other room with more hors d'oeuvres and more beverages. So let me turn it over to Tom.
Thank you. So I'll just start by saying that I didn't go to Princeton. Sorry. But my niece goes. And her father, my brother, went. And my father went. And my great uncle, so my father's uncle went. And my great grandfather went. And then I teach there, so I feel like I belong anyway. Sorry. So yes, I work in computer vision. I joined Princeton in 1998, and for a very long time worked in computer graphics, which is describing the world as in a computer as a three-dimensional scene, and maybe describing its materials and where cameras are and how light transports, and trying to understand scenes from being able to synthesize new views of them and analyzing shapes and things like that. And probably 2 or 3 years ago, moved into computer vision, which is to a first approximation the opposite, which is you have an image and you're trying to understand all those things about the scene. Within computer vision, there's many different flavors. You're probably familiar with computer vision that would happen at Facebook or in Google image search or something like that, where you have a large set of images that you've downloaded from the internet that you didn't take yourself, and you're trying to recognize faces or characterize that this is a picture of a kitchen or things like that. Make recommendations about what else you might be interested in, so on and so forth. I don't work in that kind of computer vision. The kind of vision that I work in is if you have a device that has a camera, in my case a depth camera, but we'll get to that, and it's operating in the real world and trying to understand the world around it. So that would be like a self-driving car would have cameras that need to understand where the pedestrian are on the road and everything else. A drone has cameras to understand how to navigate in the world. Your phone has cameras that if you want to do augmented reality on the phone, or if I have a virtual reality device in my head, it has the cameras to try to localize where my head is and try to understand what's going on around me. If I have a wearable device, that many of them don't exist yet, but there will be wearable devices and things like that they're operating in the real world and having to make real-time decisions about what is the three-dimensional structure of the world around me, what are the people, what are they doing, what are the objects, what can I manipulate, things like that. So that's the kind of computer vision that I work on. Of course, you're probably well aware of many of the industries that are affected by that kind of computer vision. So self-driving cars is the most obvious, but also robotics of robotic manipulation with robot arms picking up and doing things, obviously drones and so on and so forth. So it's a very, very hot area right now and very dynamic. I would say that to a first approximation, most of computer vision didn't work at all like 10 years ago. People were trying to understand, I don't know, how to track the camera or how to build a three-dimensional model of a scene, but without understanding what things are and stuff like that. And starting around 2012, things really changed. There became data sets that became available that were labeled by people with regards to what's in the image. And there's this data set called ImageNet in particular that they used mechanical Turkers, so people around the world on the internet, to label images regards to what's the content of the image. This is a cat, that's a kitchen, that's something else. And that provided enough data for algorithms to automatically learn what are the key features that differentiate this kind of object from that kind of object in an image. So cats have, if there's a little pattern that says this is a cat that's different from kitchens, the computer will pick that up and understand that. And these algorithms, how many people have heard of deep learning? Okay, some. So algorithms that, based on deep learning, which I'll describe really quickly, started to really work. And now I think sort of tasks like recognizing what kind of image this is, computers are incredibly good at that, like on par with people. And the really cool thing about that is this data set ImageNet that changed everything happened at Princeton. So this guy, Jia Deng, is the PhD student who was the person who put that all together, and he did that at Princeton. So very transformative. Yeah. So again, if you have millions of examples of images that are labeled, you can, what people used to do is they would look for patterns, like, I think cats are going to have edges that look like this, and so let me make little computer things that look at patterns of pixels and say, that looks like that might be a cat because I have a furry detector or something like that. I'm really oversimplifying. But what a deep network does is it takes the image as input, which is a 2D degree of a 2D array of pixels, and it computes what are called filters. So take some of the pixels here and do some simple math, like multiply and add on them, and then you get back a little function of those pixels, which is multiplying and adding. And then you end up with a new image, which is the result of all those little filters. And if you do that lots and lots and lots and lots of times, with maybe some nonlinearity between each layer, you end up with the ability to compute a function that goes from the raw pixels to some output of that sequence of filtering operations. And when you have ground truth labels, you can basically train a network to learn the filters that optimally differentiate the different classes you care about. And it just turns out that you have enough training data, you can learn these really, really complicated functions, and they work amazingly. Anyway, sorry, that was maybe a little bit too much detail, so that's really made a huge difference in computer vision. So 5 years ago, at a computer vision conference, there was, I don't know, 0 papers on deep learning, and now there's 800 or something like that. So it's just completely revolutionized the field. Okay, so what I do is I take in images that start with depth. So there are cameras that, like a Kinect, Microsoft Kinect, you probably have seen, that either shoot out light and measure how long the light takes to return to the camera, so that gives it a depth, or projects some sort of pattern that it can then figure out the depth by triangulation. But anyway, the bottom line is you get back an image which is a 2D array of not only colors but also depth. And from that, we try to understand what all the objects are that are visible within the camera. So these pixels are a chair, these pixels are a door, so on and so forth. But but we would like to much deeper understanding than that. You know, it's one thing to just label the pixels, but it's a completely different thing to be able to understand how to interact in this scene, like navigate through it or something like that. And so we actually use computer graphics models to generate massive training sets where if I have computer graphics models, then I can make as many images as I want from that, and they're perfectly labeled because they were computer graphics models. And so I can make millions and millions of images where I train my deep network on those, and then train on the small amount of real data that we have, and end up with these networks that really understand not only how to label the pixels according to what object they are, but also how to predict what's behind the visible surfaces. So like from my view right here, if I have from my eye has a 2D array of pixels with depths, and I can't see most of you. So your legs are not visible to me if you're not in the front row. But if I've trained on enough data from computer graphics that has scenes like this, I should be able to learn a prior that allows me to predict that you all have legs and where they are, and so on and so forth. And so a very recent project that we've done that's been very impactful has been a project where we train on computer graphics models to be able to do that task, basically predict the entire scene even though we only see part of it. And then something that we have that's coming out at a computer vision this conference this year is that given a limited field of view of an image, try to predict the entire scene, so that all the stuff that's behind you, which is a hard problem. But if you in your minds, I mean, maybe you walked in and so you got to see what was behind you, but even if you didn't, you would be able to make a pretty good prediction based on what you can see of what the whole room is, including that there are people behind you in rows of chairs, and the walls continue, and so on and so forth. And again, if you have enough training data, you can train a network to do that. So we aim for kind of understanding that's beyond just the obvious of what you can observe directly. And then I'll describe one more kind of cool project. There's something called the Amazon Robotics Challenge. So Amazon has warehouses where they have buckets that are about this big, that are full of stuff. And it's cluttered. It's like 30 or 40 objects within a bucket. They're all on top of each other. And they have people that go and pick the right objects from them and put them in the boxes for shipping and things like that. And so they would like to have robot arms do that. So they had a challenge this last year where many top research groups entered this challenge. And the goal is to be able to successfully pick up objects and put them in the right box. And it's really, really difficult because the objects are all jumbled up, and many of the objects you've never seen before. So when I talk about having lots of training data, if you got to look at a billion examples of this kind of object, then you can get pretty good at recognizing it. But the Amazon warehouse catalog, or Amazon catalog, has like 2 billion objects in it, and so you can't train on all of them. And so we got to train on like 100 of them, and then we had to, at test time, we had to be able to handle any object that you put in the bin. And anyway, so I won't get into the details of this, but again, it was a deep learning kind of situation where the feedback of whether you're going to be successful or not came from trial and error by the robot, and it learns how to pick things up by trial and error, and that's its supervision for how to train its deep network. And the short version of that is that we won the challenge. So we won. There was 2 parts of the challenge, and we won the main part of the challenge. And anyway, and it was pretty cool. It was a team that was both graduate students and undergrads and stuff like that. So it was very, very cool. Anyway, so we work on a variety of problems that are related to understanding what's happening in the world with cameras, and these days it's all about deep learning.
Thank you. Thank you.
Yeah, I was going to say, I met a few of your students at CVPR, and especially the paper that are forthcoming at the CVPR, and a lot of that research is also very applicable to what we do. So maybe I'll just start off with a brief introduction. So Bryton Shang, class of 2012, started a company called Aquabyte. One of the few companies taking a Silicon Valley approach to applying machine learning and computer vision to fish farms, of all things. Just before I start, there's other people from our team here, Lo Saxena is class of 2015 here, and also Angela Zhang, who's class of 2013, are both also part of Aquabyte. Yeah, just maybe be real, just a brief background. So, studied financial engineering. After I graduated, worked in algorithmic trading in New York, both at a fund and also started my own trading fund. After that, got into a series of startups. The first startup I started was also with another Princeton alum, class of 95. We built a platform for brand licensing. Then after that startup, joined another company in New York that was doing deep learning on tissue images. So normally a doctor would look under a microscope to diagnose what disease you have. We could take an image of that tissue, run it through a deep neural net, and be able to predict which type of cancer it was. And so I had been living in New York. That company got into Y Combinator, moved out to San Francisco to do that with them. Liked it so much out here that I stayed out here, and at the beginning of last year, had the opportunity to incubate a new company. So another alumnus, Amit Mukherjee, is a partner at NEA, and we had known each other from college and basically had been catching up with him, and he was like, why don't you incubate a new company here around machine learning, and basically gave you some money to do that, and you can work out of the NEA offices, and we'll pair you with another venture partner, Greg Papadopoulos, former CTO of Sun, to help incubate this new company. And so we have been thinking about a number of different ideas, and one of the ideas that had come from a previous co-founder of mine was that had invested in some fish farms. And so basically fish farming is one of these industries. It's not really prominent in the US, but it's massive worldwide. So $180 billion industry, fastest growing sector of food production, covers everything from shrimp farming in Thailand to salmon farming in Norway. So for example, in Norway, in the fjords, they're growing salmon in these massive pens. So we're talking 200-foot diameter pens growing 200,000 salmon at a time. And the main way that they monitor feeding, which is the #1 cost, is by sticking these surveillance cameras in the pen. And basically, people watch the footage of the fish swimming around all day and the pellets falling down and determine how much to feed based off of that. And so the big idea being if we could design a machine learning model to optimally feed, and if we could save 20, 30%, or even a few percentage points of feed, that could be a great deal. And so basically the way we thought about doing that was, okay, if we could understand the size of the fish over time, the environmental conditions, how much was fed, then we could start to figure out how much to optimally feed the fish. And so the way we do that is based on computer vision. So we kind of take similar footage off the pens, be able to analyze the footage using deep neural nets, using stereo algorithms to decimate depth, as well as segmentation, and be able to use that to gain a sense of scale and be able to size the fish. And so basically just come up with this idea, was looking at farms to pilot in California. Unfortunately, California is not the best place to do that. Actually, fish farming is illegal off the coast of California. One of my family friends growing up was a professor of aquaculture at Cornell and told me about this salmon farming conference in Norway. And so basically booked a ticket to Norway for 2 weeks, flew into Copenhagen, drove kind of all around Norway visiting the fish farms, and it was just amazing to see how the industry had proliferated there. And so while I was there, was pitching this idea to do biomass estimation, and basically what I found was there was another problem there. So essentially, sea lice is a big problem. So it's this brown parasite about the size of your thumb, and basically it's decimated the wild population of salmon in Norway. So it's 1/10 of what it used to be. And so, yeah, so last year, the Norwegian government passed a regulation that requires all farms to sample for sea lice on a weekly basis. And so there's guys going out every week, they take a net the fish, and count the sea lice by hand. And so it turns out, well, you can also recognize the sea lice from a camera. And so this idea of using deep learning and computer vision to be able to estimate size turned into a suite of different products where now we can do sea lice counting, we can also do behavioral estimation, we can do quite a number of things. And so while I was in Norway, basically set up a bunch of pilots with farms, came back to the US, around the same time, kind of connected with AEF, which also invested in the pre-seed and basically closed a seed round with NEA and Cosinoa, Princeton, Stanford University, a Norwegian venture firm, which is pretty unusual, and basically with the idea to build out a team in San Francisco to do the machine learning and computer vision, and also staff in Norway to be able to commercialize there. And so now we have kind of 4 people working out of, or 5 people now working out of San Francisco. So deep learning engineer, machine learning engineer, business operations, and then also operations and product development in Norway to go commercialize. And so we've started to build out the system, and so we're going to release the first product in the next 3 to 6 months. And so for us, it's really about once we get the first products in the water, collecting data, then the next step is to be able to test out the feed optimization. So I mentioned kind of the first products we're releasing is this biomass and sea lice counting. With the biomass data over time, we're going to be able to estimate how much we should be feeding the fish. So essentially, fish nutritionists have determined growth models, which are essentially partial differential equations, which govern fish growth. And I mean, fish are ectothermic, so you can basically model every factor that influences fish growth. And so basically that sort of ties back into the more operations research, financial engineering stuff I learned at Princeton. And so around this time when we complete this, we're then kind of go and raise a Series A. And so maybe I'll just share a bit more about that perspective, raising money. So essentially, so NEA offered to lead the round, obviously, even with that backing, going to different venture firms, they were like, salmon farming in Norway? No, like, there's no way we can add value. And so basically went to Norway, set up a bunch of video chats with farmers. And after that, really people became very interested after they saw how big the industry was there. And so basically, we ended up being 3 times oversubscribed with Kozla, GV, firm even wanted to preempt and lead the A. And so for us, it was raising enough capital to be able to validate the idea, and then to be able to then get some cameras in the water and get things going. And so yeah, it's been a really interesting journey, and I think it's one of the things I've noticed is a lot of people have the predisposition of applying machine learning to X, but I think if you really think about it from first principles, there's a larger kind of ethical implication of how you apply machine learning and how applicable it is in practice. So for example, in the cancer detection startup I was working on, you could build a model that was 97-98% accurate at detecting lung cancer metastasis, even better than a doctor, but no one would use it because that 2-3% would still kill someone, whereas my models that are 97-98% correct, some fish are overfed. And so in that sense, it's more palatable for that type of machine learning to be implemented in practice. And so I think we found a really interesting industry where machine learning affects the core value driver for these farms. And also, I mean, unless you know about Norwegian fish farming, no one in the valley is really thinking about it and how many founders are going to go to Norway to start something. And so really, really excited, and kind of it's been great to kind of be able to incorporate the Princeton community. And so half our team is from Princeton. We have one of our board members, Amit Mukherjee, is class of 2010, and kind of have a number of ties and really excited. So yeah, happy to kind of talk to anyone who's interested, and always we're looking to hire 3 more software engineers, so hopefully get some more Princeton guys on board.
Great story.
All right, Brian.
One crazy I promise to stay within 8 minutes. Can I stand up and talk?
You certainly may.
So there's actually 2 reasons I'd like to stand up and talk. I've gained about 10 pounds in the last 2 months, and when I sit down, I'm very self-conscious of my stomach. And I'd like to face my audience. That's the real reason. So had I heard your computer vision and AI 101 introduction, I would have signed up for the course. I didn't go to Princeton, but I taught at Princeton for 7 years, 88 to 95. I got my PhD in computer vision and AI at Columbia in the days when, so I had the luxury of one advisor in computer science, Peter Allen, and one in neuroscience, Oliver Sacks, who was earlier at Rockefeller and then Columbia. So lovely mentors. When you're in your early 20s, nothing more you can want than have someone who will just take you by hand and teach you. To give you an example, we had a Utah MIT Robotic Hand. How many of you know about that? Okay, one person in the audience. It's a relic. And we had a Puma 6 degrees of freedom robot. So we had the Puma robot hold the hand, the Utah hand, and screw a light bulb. So how many robots does it take to screw a light bulb? If you heard that joke, that came out of Columbia. The joy of doing that was to be able to write the device drivers, to understand exactly where the singularities of a robot are, what we today call deep learning or big data. Why is it not big data? It's the dimensionality of the data that matters and not the size of the data. Those are things we learn real hardcore by doing stuff in hand. So, Bryton, you're what, 27? I'm guessing?
I just turned 26.
26? Sorry, I overestimated the age by one. So I'm twice your age. So I had the misfortune of having to write drivers to visualize images, stuff that you can just plug and place. It was disadvantaged, 2/3 of my time getting my PhD was spent writing tools, and a third was doing work. But I'll go back to your age any day, man. To have that. Seriously, I kid you not. It was awesome. So are you raising Series B anytime soon? A bit about Artiman. We brand ourselves as a early stage white space tech investment fund. We manage about $1.2 billion. We have about 30 companies in our portfolio. And to define white space, for one, it's a branding term. It can mean anything. What we mean by it is a couple of things. Number one, we invest in companies that have a lot of science. So right or wrong, time will tell. We have not convinced ourselves to yet invest in a social media company. I mean, if Facebook drove by us twice, we wouldn't know what to do with it. We still won't. We're too old for that stuff, actually. All my partners are in their 50s, so there's some advantages, but also some disadvantages. How many venture partners here? How many above 50? All right, good, have some company. So number one has to be a lot of science and technology, which means long time to fruition. When you invest, you've got to hold it for 8, 10, 12 years, which means if something is going to go wrong, it will. Even if the idea was brilliant, the team was great, the execution was right, you can't predict when the next Lehman Brothers will collapse and money will disappear. Those are environmental factors you cannot predict. You don't know when some new embargo will be placed on China that'll take half your market away. So that means you have to reserve a lot of money for those exigencies. So as a result, you can make only very few investments. So corollary 2 of our statement, we want to invest in science, is we can only make very few investments. Fortunately, it works out fine because great ideas that translate to great companies with great science, those are not too many. If I had 10 times more capital, I would not find 10 times more innovation. I might find 3 times more innovation, but I won't find 10 times more innovation. It's not rate limited by capital, it's rate limited by talent. It's rate limited by good ideas. And while there are lots of really good ideas, there are very few great ideas. And that you can always tell this. For every Google or a Genentech, there is 1,000 companies that never made past 5 million. The land of living dead. You cannot die, you cannot live. You have enough revenue to keep going and you don't have enough to survive. That happens a lot. So we tend to avoid those. We don't always succeed, but we tend to go into those areas where we know the science and technology is strong. Likely the markets are big. It's going to take a long time. So we make few investments. Initial round, we're early stage. We're often called pre-PowerPoint venture fund. Because if you have a PowerPoint deck, it's too late often. So we come in with anywhere between 2 million to 8 million Series A, but then we reserve some 30-odd million for the life of the company. So that we can, if a company is doing well, we should not run out of money. That's the wrong time to run out of money. And the last bit is most of our companies are inherently very interdisciplinary. So for instance, we have a company in the building construction space. They are actually general contractors that build buildings. But none of them came from construction industry. They all came from chip design. And the premise was, if you can design a chip where you simulate 1 billion transistors and lay them out in 3 dimensions, and You send it to the fab and it comes back and it works right the first time. If you take a chip and simply physically magnify it 8 orders of magnitude, it's like a building. It looks like a building, behaves like a building. So why can't you take techniques from chip design, apply it to building? It's a large network simulation. We have a similar company in drug design that applies ideas. These are people who came out of Cadence. Anybody from semi-design tools industry? Can you see the logic? Just take those tools, apply it to a large network called drug-molecule interaction. You have a drug and you have a disease. The two interact at a molecular level. It's a large network. So with that, so that's to give you a flavor of the kind of companies we invest in. We have invested in only 2 AI type companies. So would somebody like to take a guess at the last count how many existing AI companies are in Crunchbase? Somebody like to take a guess? Or people who claim to be doing AI? I mean, no, everybody's doing blockchain, right? I mean, I do blockchain-based tailoring. This Victor Singh is a tailor, Sikh tailor, wearing a turban in Thailand, and blockchain-enabled tailoring technique. I made that up, it's not true. So, in Crunchbase, there are 52,000 companies that have AI technology. I guess maybe a fifth of them do. 10,000. And there's 10,000 companies doing something in AI. It ain't white space anymore. Now, so you have to look very carefully. So we invested in 2 companies. I'll briefly talk about it. We have 2 minutes left in my 8-minute. So we have a company called BoxBot. It focuses on the last mile delivery. Anybody heard of the company? Okay. How many packages FedEx/UPS actually get stolen in the US every year? Somebody take a guess?
Oh my gosh.
2 million. 100 million.
11 million packages get lost every year. Okay? So if you divide by per day, you get some idea, 300,000 packages every day. You divide by number of states, you get the idea. So number 1. Number 2, if you spend $1 in delivery, how much of that goes into the last mile? Once you've left the highway and you're in zip code 94301, stuck in traffic en route on University Avenue, how much money gets spent there?
62 cents.
70 odd cents. So 70 cents to $1 gets spent on the last mile. So this company says we want to solve that problem. So the FedEx guy comes and puts the box in a BoxBot container in that zip code. From that point on, a text message goes to the owner or the person who's going to receive it and say, respond when you're ready to receive the package, when you're home, when you want to receive the package. And at that point, a little robot device will step out of the box. And all of this is enabled by computer vision. It's a simple problem to solve. It's not that difficult. If Amazon packages can be sorted in a random bucket, this is an easy problem to solve. So that picks that bucket in that robotic device and goes on University Avenue, makes a left on Cowper, right on Hamilton, arrives at your address. I'm getting to my home this way. And then you step out, and then you punch in a code, open the door, take your box, go home. They solve that problem. So it's a very simple problem, very simple AI, very simple computer vision, but it's solving a real problem. If you take the total delivery cost of Amazon, how much is that? Somebody like to take a guess?
500 million? Oh, wait,
It's been more than
25 billion.
10 billion.
$17 billion, the shipping cost. So just imagine 70% of that goes in the last mile. You can figure out the TAM, technology, all that good stuff. Wow. Okay, that's one company. We've invested in a second company where, in terms of the application area, I'm not very proud of it. It's used in defense. It's got a camera system that integrates visual camera, so plain bright field imaging with infrared and now sonar. It does all the things that you said computer visionists did 30 years ago, camera calibration, the type of problems BDU solved in EE at Princeton some 30 years ago. They solve all those problems, register those images, and basically to a soldier, give an integrated image, even in the dark, on your crosshair, and then you do what you need to do. Of course, we are trying to promote this in other areas as well, which are in peacetime use of wartime technology. Final, my area is healthcare, and so hence AI in healthcare should be commented on at least for a minute. I'll give a quick analogy and go sit down. Google car, you've stuck behind one, the self-driving car? You've stuck behind one ever? Okay, somebody has. So Google took 2 million miles of learning by their admission, 2 million miles to get to a state where you can drive an El Camino Real when it's not raining and follow the road. To their admission, it will take 30 million miles to get to human performance. Perfectly understandable. Learning from scratch, 30 million miles. Why is it that our my wife is sitting there in the audience there. We have 4 kids amongst us. They all got their driver's license after 100 miles. One failed once. And after a couple of 100 miles, they got their license. And after 3,000 miles, they were able to drive well. And at about 30,000 miles, you can deal with most situations. I drove in Fargo, North Dakota. Just imagine this Indian dude, you know, wearing a turban. I don't know. They've never seen one. They've probably never seen another one. So 30 million miles. Why? Why is there so much delta? We've got 7 million years of evolution helping us, where all we learned was pattern recognition. To escape a lion, escape a snake, find the food. That's all we learned. And we can redeploy that learning to do computer vision. Now, everything who says about IBM, I mean, anybody who has worked at IBM or IBM Watson or anything like that? Okay, please don't hold the following against you or me for that matter. The claim was we learned to diagnose breast cancer from scratch, a cancer. And there's, as you know, no 2 cancers are alike, multiple hundreds like that. So if you want to simply extrapolate based on the Google example, given the dimensionality of breast cancer data, how many images will it take to learn to diagnose breast cancer from mammography? Take a guess. From scratch. 8 billion.
Billion?
8 billion. So, because there's so much variability, there's so much heterogeneity, you will need 8 billion images, back of the napkin calculation. So everybody, man and woman in this planet, will have to have cancer for us to just have learning sample. It's stupid. Cannot happen. So let's not make claims that are totally ill-founded. But can breast cancer be diagnosed? You gave the example. You can get to 97% accuracy. You take the super duper experts, take their knowledge, use them for training samples, and then of course you have something to build on. So with that, I'll rest my case. Thank you.
Great, thank you. I can't beat Ajit, but I do like the idea of standing up and speaking and be able to see everybody. I've been working with Ajit for maybe 5 years now in some of his companies, and Ajit, as you know, is just an amazing person. Where I come in is working with basically universities and inventors and entrepreneurs. I'm an IP lawyer, so I do a lot of startup work. And what I like to say is that every startup, at least every tech startup, knows something, and it's usually some kind of technology that nobody else has, in order for them to get the kind of funding that Ajit and his colleagues are willing to invest in. And so you need to protect that with the intellectual property, with the patents, the knowledge. I mean, IP is nothing more than something that you own and can control that nobody else does. So I've been working for about 20 years in IP. Before that, 10 years. Tom and I, we actually worked at the same place at one time at Bell Labs many years ago. And but since then, I've then moved from engineering into intellectual property law. And the students and the startup companies and the entrepreneurs that I work with, they all realize that in order to control and to own innovation, I mean, there has to be, usually we're talking about is filing patents. And so that's typically the kind of thing that I work on with all different kinds of companies. Just a show of hands, inventors who have patents in the audience. Great, look at this, about half. Holy cow. Hein, what do you have a patent on?
Storage.
Storage, okay, data storage. Yeah. Fantastic. And Matthew, you raised your hand.
I have a lot, about 18 patents. A lot of them are on automatic speech recognition.
Oh, awesome, awesome, very good. Now, who owns them, Matthew? Not you, the company, right? The company. Well, that's the thing is that the company needs the control, right? And this is what we work on. Tom, I'm curious. Did Princeton file a patent on the deep learning stuff that you know? Okay. So Princeton kind of let that go to public, right? That is
well,
public.
To be fair, Princeton allows professors in general to make the call about what they want to try to patent and what they want to just release publicly and stuff like that. And then everything that's come out of my lab in the last 20 years, we've just made available to the public for commercial reasons, for everything. Just my goal is to increase the knowledge in the world, not to profit off it. Sorry.
Well, that's okay. That's great. Tom is the open source model of innovation. Let's just get it out there. But that's good. That is really good. But if you have any of your grad students thinking, oh, I want to do a startup, okay, and I do some work with the university on the Office of Technology Licensing, And then what they'll say is, yes, if you want to do a startup, you need to own the thing that you're trying to develop. You need to own your innovation. Right. And so go to John Ritter's office, right, down at 93 Prospect, walk into his office and say, okay, we need to protect this. And what I tell everybody is, file your patent first, then you publish, right? Because as we all know, number of innovators, number of inventors in the office, in the room here, they know that, you know, the publication is just the opposite of patenting. Patenting, you keep it secret initially, and then you do a deal with the U.S. Patent Office, which is a deal with society saying, okay, I will disclose the invention to you, and in exchange I get this 20-year exclusivity. So I'm curious, also in the audience, entrepreneurs. How many entrepreneurs in the audience? Okay, well, the same people who raised their hands for patent. So the entrepreneurs, there's a large cross-section between entrepreneurs and also folks who are inventors. One of the things that are really important is, at least for for the white space type investments that Ajit is and his colleagues are interested in, is if you identify the white space, you want to be able to control the white space. And so for the same reason, it's important to figure out what to invest in when it comes to your intellectual property. And so, it's so easy to think of 1,000 inventions around, for example, Aquabyte, right? I mean, take your company, for example. You can think about, there are camera systems, there's algorithms, methods of determining what's a food pellet for the fish versus what's a fish, or what's a food pellet and what's this lice creature that you described, which sounds really gooey. Anyway. But there's so much that you can imagine, because patents are really nothing more than the protection of the solution to a problem. Right? Now the question is, you're constantly solving problems every day. What solutions do you invest in? And patents, as we know, are not cheap. They are expensive. I make a living, writing patents and designing patents for companies. What do you focus your patents on? What is your patent strategy? And that's really important, okay? And what I contend, and I was at Princeton on Friday, right, with Wright at the Tiger Launch event, and talking to the student entrepreneurs about what do you invest your precious funds. You have your seed capital, and it's important to think of it. You do want some control. You do want your IP. What do you invest in? And what I said, do you remember what I said? You invest in that which the world is going to be a path to your door for.
That's what you said.
That is the solution. So, imagine yourself with your startup company. In a couple of years, you're wildly successful. And the world is beating a path to your door for it, your product, your service, whatever it is, and that's what you focus your IP on. So that's pretty much what I do. And with that, I will sit down. Thank you.
Wonderful set of perspectives by each of the panelists. Thanks very much. So let's open it up to the floor. I've got a microphone. We'll pass it around. We'll take as many questions as we can. And we'll start right here.
So I have a very simplistic question to ask Thomas, actually. It sounds very interesting what you're doing with computer vision, but can you use the same thing as a wearable device for a blind person to see what we see, or at least part of what we see? And have you used it?
Yeah, so that's a great question. So a very unique Princeton thing is that every student does an independent work, or if you're an AB, a thesis. And three semesters ago, my teaching role was to advise 12 of these undergrads doing theses. And I gave each of them a camera that observes both depth and color, and asked them to think of cool things to do with it. And a couple of women were from the track team, and so they pointed these cameras at you when you're on a treadmill and tried to understand whether you're going to get hurt with the gait you're using. One was on the ballroom dance club and used the cameras to give feedback to a person with regards to their form. And one of them put a depth camera on a bike helmet and had the camera be basically the eyes for this person that's blindfolded, and then piped sound into the ears of the person to give them feedback about navigating through the scene. And it was an extremely interesting project because everything I described to you about understanding what's happening in the world is relevant here. But there's also this interesting thing about what is the sound that you provide to a person so that they can understand what the computer is trying to, what the computer sees. And anyway, it's an incredibly interesting project. And so that's a great use case for this kind of technology. I did have an undergraduate who did that for their thesis.
Did it work?
It's one of those things where trivially it works in the sense that if you just do a mapping, the computer can see depth, right? So if you just do a mapping where you make little sound sources so in front of me, I can imagine that every pixel is somewhere out in 3D space because I know the depth, right? The ray through the pixel ends up somewhere in 3D space. So if I make little sound sources at each of those places and then spatialize them, then I basically am hearing as if there was a little speaker on every little piece of the surface. And yes, I can perceive things from that. But there was this interesting thing of do the pitches and the frequencies change depending on how close they are and stuff like that. And so yeah, it absolutely provided a sense of where everything was, and you could navigate blindfolded through the scene. But there's still a lot of unanswered questions about what's the right mapping from visual to audio. Yeah. Anyway.
Yeah. A lot of advancements in AI seem to relate to labeled images and others that have been done by actual people. Is there a plateauing that we're going to have as those labels sort of run out, and do we need to find a way to automate the labels to advance more quickly?
Let me take a quick shot at that. So so a lot of the advances in computer vision have come from what's called supervised learning, where there are labels that give you the ground truth for something, and so you know during the training phase whether you predicted it correctly or not. In the last 3 or 4 years, there's been a lot of work on what's called self-supervised learning, where an example of that was if I give you 2 images from different viewpoints, and what I do is I train a deep network that will predict what the other image is seeing. And if I just have pairs of images without any human labels, I still can say, okay, did it predict correctly? And if you have lots of those images, then you can learn something that will predict something from a new view. Or if I have YouTube videos and my task is to predict what's going to happen and what the image is going to be in 5 seconds or 2 seconds, I have infinite training data that's not labeled by a human. But if I can do that task, then I have to understand things about moving objects and how the world changes as I move my camera and things like that. And so there's something called self-supervised learning that's become quite popular. There's also something called reinforcement learning, which is I'm doing a task, and if I'm successful at that task, then I get feedback that I've done a good thing. And so the robot picking thing that I talked about is done with reinforcement learning, where a robot looks at the scene, decides how to grasp stuff, and if it's successful, then it says, okay, that was good, that's my supervision. And if it failed, then that's bad. I'm going to change my weights in my deep network so I'm more likely to do well. There's another project where we've done where to have a robot automatically navigate through a scene. And so the input is an image, and the output is move forward, turn right, turn left. And it can learn how to find the kitchen and things like that, just from it can do training on its own for hours and hours and hours and hours and hours. And so it's not just about supervised learning now.
I'll add a little bit to that. So it's not always necessarily that you have to do extra data just to label and get these labels. From a startup point of view, it's actually advantageous to be able to design a human in the loop such that you naturally generate training data as a byproduct of use of your product. And so, for example, for us, when we have detections of sea lice, the low confidence detections are triaged into a separate queue, and those are annotated by actual operators that maintain and ensure that the algorithm is working. And so in that case, you don't actually have to spend extra time to annotate the data necessarily.
So computer vision can be used for a lot of good things, but in China they're creating like a surveillance state, and you can imagine killer robots. So I'm just wondering, have you all thought about the potential for abuse, and in what ways computer vision can be used to potentially harm society?
Wow. Look, the question is generally true, right? Any technology has the potential of harm. So all you can expect is there's enough checks and balances in the system, in the legal system, in the judiciary, in the general moral, ethical fiber of the society that'll prevent that from happening. So that's a broad assumption. And by and large, it works. By and large, it works. There's corruption everywhere on the planet. There's corruption in Uganda, Kampala. There's corruption in the United States. It's called campaign financing here. It's called right there. It's the same freaking thing. So the corruption is everywhere. But despite all of that, by and large, the moral fabric of society is pretty intact. We don't go about killing young kids and burning them on a pile. We don't do that. Now, of course, is there potential for abuse? Of course there's potential for abuse. Every technology has potential for abuse. So I don't think you can rely strictly on technology to self-correct. There was a discussion I had with somebody at Stanford, and he says, well, can you program doubt? Can you learn to doubt yourself? Can you learn to... How do we get self-aware? By doubting ourselves, by questioning our judgment. Then we validate, we triangulate, and we become more self-aware. And then through that comes some higher order understanding of who we are and why we're here. Will machines get there? Well, I mean, the difference between science and art will remain, and so will the difference between machine and human. So I don't think the answer comes from machine or technology. The answer will come from, will humans retain their moral fabric? And having watched 6 episodes of Star Wars back to back, one of my daughters would kill me if I get one thing wrong. I think I have a strong belief it'll remain intact.
Yeah, I mean, I would also add to that. So essentially, I mean, with, for example, more advanced deep learning algorithms, being able to have explainability and clarity into how the model is actually making decisions could cause inherent bias in your model. And so there's this sort of kind of field of, okay, how do we apply ethics to machine learning? And so to give one anecdote, I was at one of the NIPS conferences, and basically they were giving a presentation on how they had decided to make a neural net to be able to figure out how to treat some patient. And basically they had the choice between using this linear regression model, which was very straightforward, and they built this neural net model which actually performed better. And so you would think it would be necessarily unethical for them to use this better performing model, but actually what they found is this model systematically biased against certain populations. And so that's to say that necessarily you wouldn't necessarily treat the model to make a correct moral decision. And so I think this kind of can be extrapolated to kind of other parts of computer vision machine learning. And so I do think it is a valid concern, and that's also why you also see other organizations like OpenAI that are trying, and Google, that are open sourcing their technologies and trying to promote machine learning such that machine learning isn't necessarily consolidated in one big entity.
Can I say one thing? There's a project in the computer science department at Princeton right now about fairness in AI. It's quite a large project that is studying exactly the biases that learning from data produces. So if you do a machine translation and you kind of translate Tom Funkhouser, maybe all the examples are like stupid Tom Funkhousers, all comes together in all example text. And so if you translate, it might always output stupid Tom Funkhouser because the data was biased that way.
Yep.
And so there's quite a significant project at Princeton going on that right now. I'm sorry.
Hey, so Professor Funkhouser, you mentioned reinforcement learning, specifically deep reinforcement learning. I've heard a lot of people describe it as like where deep learning was like 5-10 years ago. I was wondering, like, if, in your opinion, what are the potential steps forward to make it like more repeatable and more sample efficient and whatnot?
Sure. So that's a pretty specific question. So reinforcement learning again is that I can by trial and error get feedback about whether or not my predictor is good, and I can adjust my predictor based on whether I'm successful or not. And it is true. Like so, the example I told you about navigating through a house and finding a kitchen or something like that. It takes the the agent 1 million episodes of navigating. It starts just randomly moving around, and then eventually it kind of learns how to make progress, and then eventually it learns how to find kitchens. And it took 1 million examples to do that. And I would say that most deep reinforcement learning things are like that. This robot arm thing that we did takes 2,000 examples, and it takes 2 hours on a real robot of real time to train the thing to be really, really good. And it's all about the parameterization you choose for your problem. And I don't want to get into the details of it, but this one, most people would parameterize that by the angles of the robot arm, the joint angles of the robot arm, which is a very complicated space. And we parameterize it based on the affordances of the objects in the 3D space. And it just turns out that that's a very easy function to learn, and then we can back into the joint angles to get the robot arm hand to the right place. And it's incredibly sample efficient. So I'm sorry. Yeah. Anyway, so it's people are figuring this stuff out.
Yeah, it's reminiscent of the deep drive paper by Shang. Yeah. Cool.
I'm a history major, so I'm way out of my league. I'm interested in the panel's opinion about the ethical issue that I think we are vaulting ourselves into, where things that were bad that used to happen because of human beings who are flawed, because of life that happens, were kind of easily explained away, except if there was malintent. But now we're getting into a phase where if someone is programming how a car drives, that car needs to decide whether, to hit the old lady crossing the street or the truck that's coming into it, et cetera. So now these things that used to be just part of chance in life now become decisions that somebody needs to make. And I don't know if this is the legal, Full Employment Act, because, we're going to be legislating ourselves until, we're all dead. But I'm interested in how you guys are wrestling with that.
So we designed a system in New York City some 30 years ago, where a system would learn the rules of traffic light just by observing what we do. So after several thousand episodes, the system learned the following: red, stop; green, go; orange, speed up. That's what it learned. So now that you can take it any which way. If somebody is physically programming, which is unlikely to happen in a learning-based system, then of course there's ample room for malfeasance, malintent, all of that being programmed in. And there you rely on checks and balances. There'll be a doer and a checker, or there'll be a spot check, there'll be a bad check, something like that. But if it's a machine learning system, you are clearly learning from examples which are being guided by humans. So you will learn human errors as well. So, for example, in the earlier IBM Watson example, I commented once that if you're learning the average of all oncologists, your patient is in really bad luck. Learning from a group of people, learning the average. I would like to be an average investor. Figure that. Why would I like to be average? I'd like to be above average, or way above average. So learning from an average of people is a very bad idea. So which means if the system simply learns from an average of human performance, you're up for trouble. So which means these systems will have to evolve where there is programmed learning of best practices and then de novo learning. And I think eventually, so I'm, by the way, my partner Brian Wilco at Artiman is a history major, and he's got the highest success rate so far amongst all best science majors. So yeah. So I have strong faith that these things sort themselves out over time. Look at progression of any technology in the last 100 years. The good news is there's ample competition, and competition usually determines that best practices win. It almost always pans out. So I have a strong faith in that system.
I think your question is changing. It used to be that people were hand coding, if you see this, turn left or whatever, and now it's all from data. But so now the equivalent of hand coding the decision is about which training data you give it. Anyway, so it's changed a little bit.
And the point of bias you made earlier.
Yeah, exactly.
So in fact, one of my daughters pointed out that there was a system learning something about dynamics, group dynamics at work. And the images that were available in group settings were very male dominated. The ratio of male to female was highly skewed towards males. And the learning that the system garnered from there had a lot of inherent biases that are actually already there in the society. So now we're creating a system that carries the same bias as the society does. So again, competition sorts this out. That's the good news about competition. It always sorts this out. It's not a very efficient system, but it's a robust system. So if you think about things that were designed versus things that were organic, look at life, look at human body, look at the amount of resilience, redundancy, robustness built in by sheer process of emergence, a sheer process of organic behavior, versus a system that is designed has so many single points of failure. Take a computer chip, take a clock, take a car, take a chair. I mean, this damn thing, you can almost never get it right. I mean, your back always hurts when you sit on a $1,000 chair. Too many single points of failure. If chair was evolved over 1 million years, I bet you will be right. I've never found the right briefcase. I've never found the right chair. Has never yet.
I'd also add that I think society is evolving to meet the needs of machine learning as well. So to give one example, in the autonomous vehicle space, it seems like they're treating the status of self-driving cars as common carriers, and so no longer treated under tort law where it would be an individual, but more treated as if it were a bus carrying a group of people. And so I think you see evolution on the society's aspect to kind of react to different innovations in machine learning.
Yeah, but there, honestly, the beauty of U.S. Constitution plays out. I mean, 200 years, simple, very simple, 8 pages of writing, and most of it still applies. With only, 26 amendments? Or something like that. It, by and large, still applies. Property law plays out into intellectual property law almost just fine. By contrast, Indian Constitution is 1,170 pages. Everything contradicts everything else. It's so specific that we almost have to modify it.
One last question.
Thinking with a black hat on, you're going to develop a system with a set of training images, and you're going to go out with hopefully a successful product. If I wanted to come along and design a system that would reliably defeat yours, and I have access to that same amount of data, is the effort to do that on the same order of magnitude, or is it much more difficult?
Oh, wow. Wow. Good question.
Yeah.
Ooh. Professor?
I don't know. That's a good question. So learned systems are good at encountering situations that are like the training data they've seen before. And so the reason that autonomous driving, for example, is so hard is it's pretty easy to do the right thing 99.999% of the time, but if there's never seen a plastic bag on the road in front of you, you don't know whether you can drive through it or whether you've got to avoid it at all costs like a baby. And so there's just all kinds of weird cases that you can encounter that are very unlike your training data. And I kind of disagree with your analysis on the number of miles required, because cars can run in parallel, and every new car gets to start from the training level of any car that's ever seen anything. And so if you need 50 billion miles or whatever the number was, you've got lots of cars. You've got millions and millions of cars doing those miles.
They can happen in parallel, but you still need those many miles.
Tesla, for example, captures all the data and sends it up. And so they basically, Tesla collects the weird cases, and that's, they get sent up. All the normal cases, the data just gets thrown away. So how much, so I think the way to defeat these systems would be to put them in situations that are unlike they've ever seen before or ever been trained for. And I don't think that would be very hard to do now. 50 years from now, if 100 million cars have been driving for 50 years, maybe there just won't be that many weird situations you can put them in. I don't know.
With that, I want to just thank Tom and Brighton, Ajit and Jeff. Thank you very much. A round of applause for everybody. as a small token of our appreciation, a gift for each of you.
If you can identify the gift.
Oh, a tiger. Thank you.
Okay, to wrap up, just a reminder about some things that are going on, because the calendar of entrepreneurial events seems to be expanding both geographically as well as in depth. And I think this panel discussion was reflective of that. I will just share with you a couple of things. One, show of hands, who's going back to reunions next month? So for those of you going back, there's going to be a mini entrepreneurs conference on Friday morning. Some really exciting topics. More information coming out on that shortly. But there'll be a series of panel discussions on some really interesting topics, including things like smart cities, more information on blockchain. Maybe I can twist Tom's arm to come back and talk about computer vision. So that's one point. And the second item that's actually not on the list, but I mentioned earlier that we're going to hold a conference here in the Valley probably next spring. I encourage anyone in this audience or other fellow alumni who want to be involved in the planning, in the, just the thoughts and efforts that go behind all of the topics. Please, if you have any interest in playing some kind of role, I encourage you and invite you to join me and a small team that we have at Princeton to do so. If you also are aware of space that we might be able to have donated to support that conference, that would be also, local knowledge is always helpful. So if you have any ideas, please share that information with me as well. So the final person on the agenda is Michelle Gannon. I asked Michelle to join us. Princeton Alumni Angels was a co-sponsor of tonight's event. And as I also mentioned, there's now an event in New York City that was occurring in parallel to this one. And I wanted Michelle to share with everyone the exciting progress that the Angel Network has accomplished. Michelle?
Hi, my name is Michelle Gannon. Oh, there's a little obstacle course to get over first. And I'm one of the founders of Princeton Alumni Angels, and I also head all of our marketing endeavors. Basically, Princeton Alumni Angels is a way for us to grow our alumni entrepreneurship ecosystem. We felt as if there really wasn't a whole lot of entrepreneurship, especially 7 years ago here in this area, and yet this is an area that is filled with business and ideas and startups, and yet Princeton didn't have a presence a couple of years ago. So we started this, and we do a series of events like this one, panels, but our big events are the pitch nights. And our main goal of the pitch nights is to grow this family of investors. Our pitch night, we just had the pitch night here in San Francisco, and as Don said, we are doing the exact same companies in New York City. We had 80 companies apply, and we picked 6 from those 80. The event was extremely successful. We had about 70 angels attend, and every company had about 10 or 20 angels that were interested in investing. And that doesn't even include New York. So right now they have 200 people who are listening to those 6 companies pitch in New York. And so I'm sure we're going to have these kind of robust investments, as well as the idea that they're just exciting companies. So if you're interested in finding out more about Princeton Alumni Angels, please take a look at the website that's getting passed around on the little sheets of paper. It's princetonalumniangels.org. And on there, there's a way for you to sign up, so please sign up if you're interested. If you're interested in being a startup with us, we're planning on having another round in the fall. So please submit whenever you're ready. But also, if you're interested in being an angel, please sign up for our newsletter on that page as well. We're planning on having a lot of events that are also not so formal, events in people's homes that angels can kind of get to know other angels and bring investment opportunities to each other. Also, if you're interested in some of those fantastic 6 companies and we're not able to attend the event, please go on the website and you can request a password in order to get access to the decks. After New York, I'm also going to put up the video of each of those 6 presenters so that you can see the pitches, you know, and enjoy them in your own home in your pajamas, if you'd like. So if you have any questions about Princeton Alumni Angels, please reach out to me. I'll be here kind of milling about. But generally the idea is that it's exciting. It's exciting to see all of these Princeton-led companies that are coming out of the woodwork here. We're not all consultants. So enjoy your night and thank you very much.
Thank you. Okay, you've been a great audience. We're going to serve more appetizers and hors d'oeuvres and beverages out in the reception area for another 45 minutes or 60 minutes. So continue the great conversation, and thank you for joining us tonight.
And let's thank John for organizing that.
Thank you, John. Enjoy.
Thank you very much.
Michelle.